home and listen in. Don't do it like in bed because you'll just fall asleep. But they're there if you want them. Okay, so you got to avoid the unnecessary information and just focus on what you need, where you're starting from, and where you're going. So a 12-ounce can of cola contains 12 teaspoons of sugar. A lot of times, one way that you could do this wrong would be to do that 12 ounces right at the beginning of the question and just assume that you need to start with 12 ounces. And you can do that. There's still a way to do the question, but it's easier if you keep reading and think about what we're really trying to convert here. So 12-ounce can contains 12 teaspoons of sugar. If each teaspoon has a mass of 4 grams, how many pounds of sugar will a person consume per year if he drinks 2 cans of cola per day? All right, so that's a lot of information. So first thing always to pull out is, what should your answer be? Where does it describe what your answer should be? Which phrase? Pounds of sugar will yeah, how many pounds of sugar? That's going to be our answer.
Tiny bit more. Oh yeah, pounds per year, I think, right?
Pounds of sugar per year, yeah. So that means that our last answer should be, technically, like you said, it should be pounds per year. If you just said that the final answer would be pounds, that's also okay because it's pounds per 1 year and it's just asking about 1 year. So it's probably going to be okay. It's going to be correct also. But technically you're right. It's pounds per year should be the answer. All right. So what are we starting with? What kind of a unit are we starting with? Yeah, well, we can start in a couple places. We can start in grams per teaspoon. Okay. We can start in teaspoons per can. I think it makes most sense here to start with teaspoons per can. And the reason is this. Each teaspoon has a mass of 4 grams. So let's start writing down some equalities here just because I'm getting confused just talking about it. So 1 teaspoon equals 4 grams, 4.0 grams. 1 can equals 12 ounces. And also 1 can equals 12 teaspoons of sugar. Okay. Other things we see here, of course, the ones that are given, and that there are 2 cans in 1 day for this particular question. So these are all the equalities or the conversions that are given in this problem, which means that we can switch between any of those units at any time based on setting up our multiplication thing. Other ways that you might do this is you might have simplified it for yourself. So you might have said, okay, well, each teaspoon is 4 grams. There's 12 teaspoons. So I know 12 times 4, 48. So each can has 48 grams. And just start there. Anybody do that? A couple people. So that makes your conversion a little bit shorter and a little bit easier. That works too. But let's assume that we're going to do this all out as a big string of conversions just to kind of see how it works. So those are my equalities. I know I have to end in pounds per year. And so I'm going to be starting in, let's say, teaspoons per can. Does that make sense? That I'm starting with 12 teaspoons of sugar per can. And then I've got a certain number of cans, and I've got a certain number of days, and a certain number, and then eventually we're going to get to pounds. So we want to get teaspoons to pounds and cans to years. Everybody see that? The top of the formula is going to go teaspoons to pounds. The bottom is going to go cans to years. So how do we get from teaspoons to pounds based on those different equalities that we wrote down? What's the path there?
Change teaspoons to grams and grams to kilograms and kilograms to pounds.
Yeah, that looks like it works. So we could go teaspoons to grams by that first thing over here. Then we can go grams to kilograms because we know all of our metric conversions. And then we can go kilograms to pounds from this right here. So we look at the different equalities we have and we figure out how we can get from one to the other using those equalities. We can set up the equations later. All right, so then what about the bottom? Cans to years. How do we do that? Yeah. Yep. Cans to days, days to years. We've got all those as well. So cans to days, days to years. Don't worry about the fact that these conversions don't necessarily make sense. Like number of cans isn't the same type of a measurement as number of years. Just like teaspoons to grams is not like exactly a conversion. But because we have these equalities from the question, we can do that. We can switch those units. All right, so now we have to switch. Now we have to set up our equation. At each point, we're going to cancel things by having them on the opposite side of the fraction. And just to keep everything straight, let's do one side first and the other side second. So let's do the top first and then the bottom second. So we'll start with 12 teaspoons per 1 can. And then let's multiply by factors to get us from teaspoons to grams to kilograms to pounds. So that's going to look like this. Teaspoons to grams, grams to kilograms, and kilograms to pounds. See how that works? Cancel teaspoons, cancel grams, cancel kilograms, and we're left with pounds. Now we just have to fill in those numbers. So our equalities tell us 4 grams per teaspoon. We know from our metric system 1,000 grams in a kilogram. And from the question, we're told 2.2 pounds in 1 kilogram. And now we don't have to stop there. We can just do the bottom. So let's add the bottom on. We'll switch colors so we know that we're doing something different here. So now we're going to go cans to days. Notice that since the can started on the bottom, we need our unit on top in order to cancel that now. And then days per year. And we can fill those numbers in as well. So 2 cans per day and 365 days per year. Let's check to make sure those cancel. So we've got cans and cans, days and days. And so we should be left with pounds per year, just like we want. Make sense? All right, let's evaluate it and see what we get. times 4 divided by 1,000 times 2.2 times 2 times 365 is 77. We've got 2 significant figures. So by the end of that year, you will have consumed 77 pounds of sugar in your cola. Yeah.
Is there a reason why you divided by 1,000 before you finished multiplying the tops?
Oh, no, I just was going in order.
Oh, like
you can do the tops and then the bottoms, or you can, because multiplication and division are commutative, which means, or associative, I guess, so it doesn't matter what order you do them in.
Does the same thing in order of operations order, so it doesn't matter which order you do them in.
Right.
Right.
So you can, so however you keep it straight for yourself, you can go from left to right, multiply and divide as you go, or you can go like do all the tops and then all the bottoms.
Okay. And then how do you know like which number to use for significant figures?
Good question. So let's look at all the numbers we've got and think about the measured numbers versus the exact numbers. One key is going to be in the question. So something like 12 ounces, a 12-ounce can, that's a measurement. So that's 2 significant figures. 12 teaspoons of sugar, there's another one, 2 significant figures. 4.0 grams, that's another one like that. 2 cans of cola is not a measurement because it's an exact count, 2 cans. So that's like 2.000 cans. So we don't use that for significant figures. We could, I guess, but in this case, I would say that makes more sense as an exact number. And then our conversions, anything that is an exact conversion, like 2 cans in a day or 1,000 grams in a kilogram, 365 days in a year, those would be considered exact numbers. Although I guess technically there's a little bit more than 365 days in a year, so maybe that's a measurement. I'm not sure about that one, but at any rate, 2 significant figures is the order is the one for here. In general, I mean, these types of questions are not written to fool you on significant figures usually. So if you see some measurements or some decimals in the question, that's usually a good indication of where your significant figure should be for these types of questions. All right, sound good? Everybody feels good about conversions? All right, while we're talking about conversions, before we get into the new stuff, I had a couple questions on one of the mastering chemistry problems. If you have any other ones, please let me know. The first assignment is due soon.
Is it Friday 11:59 or Thursday 11:59?
Let me check that.
I think it's Friday, 11:59.
I think it's tomorrow night. Yeah. Let me check to make sure. Yes, tomorrow night at 11:59, and then the adaptive part is due Monday. So, if you can't get that done in time, let me know. We'll move back. Yeah.
So I could skip that. It didn't even let me take it.
Right. If you get more than, I think, 90% on the homework, then you don't need to do the adaptive part. You just get full credit for it. All right. Does anybody remember which number that lead question is?
No, it was definitely nearer to the top.
Near the top? One of the first ones? I may have it here. Let's see. I wish they would tell you.
Definitely in the first half. I know that. I think it was somewhere.
Is this one? Yes, this one. Okay. Let's copy this over to our, we'll just go through this together. So part of this question is about how do you deal with percentages in a conversion question like this? What does a percentage mean? Okay. Can you read that okay? Too small? Just gonna make it skinnier. All right. Lead metal can be extracted from galena or galena, which contains 86.6 lead by mass. A particular ore contains 68.5 galena by mass. The lead can be extracted with 92.5% efficiency. So what mass of ore is required to make a lead sphere with an 8-centimeter radius? So let's think about what's happening here. You want to make a lead sphere, so you want a certain amount of lead. But in order to get the lead, you have to extract it from the galena. In order to get the galena, you have to extract it from an ore. So you're losing a little bit each time. So what amount of ore, large amount of ore, do you need to start with so that you can lose a little bit each time and eventually get to a lead sphere with an 8-centimeter radius? So that's, and you need a little bit more information here because we need the density of lead. So let's see if we can do this. So first of all, you need to remember your high school geometry. And I won't make you remember this for exams or anything, but since it's homework, you can always look it up. How do you find the volume of a sphere?
4/3 pi r cube.
Yeah. So volume of a sphere is 4/3 pi r cubed. How many people thought they'd never have to see that formula again? People. Yeah, sorry. Okay, let's fill that in then. So our radius is in 8 centimeters. What is 8 cubed? 112. times pi, we only need 3 significant figures, times 4/3, which is 1.333. So that's going to be 2,140, or we'll say 2.14 times 10 to the third cubic centimeters. So that's going to be the volume of our lead sphere. Again, that's not a formula you need to know for this class. Remember it, great. If not, I'll give you that kind of thing if you need to do that in an exam. Okay, so how do we get to mass from this? We've got a volume of lead that we need. How do we know how much mass of lead is in that volume?
We need the density of lead.
We need the density of lead, because density is going to give us grams per cubic centimeter. So does anybody know the density of lead? Maybe look it up? No? All right, let's look it up. Is it in the book? Let's just assume it's on the internet. It's always a little dangerous, but what do you think? You think Wikipedia's got the correct density of lead? Why not? We'll try it.
For the sake of this.
For the sake of this problem, it's fine. Yeah. You can always check in Mastering Chemistry and see if it comes out right or not. So 11.3 grams per centimeter. Density of lead, 11.3 grams per cubic centimeter. Okay. So we can convert this now. 2.14 times 10 to the third cubic centimeters of lead. And we want to go from cubic centimeters of lead to grams of lead using the density. So the number of the density, whatever that is, always goes with the grams because it's that many grams per 1 cubic centimeter or 1 milliliter. So if grams are on top, you put that larger number on top. If grams are on the bottom, you put it on the bottom. All right. So 24. By the way, when you do this problem, you can actually set this up as a whole big conversion thing, starting with after you've done your volume. So you can go cubic centimeters to grams of lead to grams of galena to grams of ore, whatever. But we'll just do it step by step here. And also, I'm not going to tell you the whole thing, so you can figure out the rest of it. But I do want to show you how to set it up. All right, so that's kind of, we've got our grams of lead. And this is how much we want in that final sphere. So that's how much lead we want to end up with. Which means that the amount that we're actually going to, the mass of ore should be a much larger number because we're losing some each time based on those percentages. We're going to keep that in our heads because if we do all this and then we end up with a smaller number, we know we flipped some stuff around. We have to go back and check it. All right, so how do you deal with something like this? Anybody come up with a good way to do this? Yeah.
Make it a decimal.
Yeah, you could make it a decimal. But actually, and yeah, that's basically what we're going to do. But thinking about it in terms of a conversion factor, you could also do what?
I actually have a question.
Oh yeah, go ahead.
A much higher number, so this is times 10 to the third.
Oh yes, thank you. Don't want to leave those things out, right? Yeah, that's 224,000 grams of lead. Thank you very much. So what we can do with a conversion is we can say 92.5% efficiency really means that for every 100 grams of galena, or what do we end up with?
Shouldn't we clean over lead just so it gets us out?
Well, we've got two different steps of
For every 100 grams of galena, shouldn't it be 86.6 lead? It says galena contains 86.6.
right, but there's two different steps here. So let's see how we're gonna. let's write all these down so we can, so a percentage is percent, which means per 100 of something. That's what percent means. So we can set that up to look like this. As you're saying, every 100 grams of galena has 86.6 grams of lead. Every 100 grams of ore has 68.5 grams of galena. All right, and then finally we have to deal with this efficiency thing. So that means that for every 100 grams of, we'll just make up a new unit and call it lead from galena. We only actually get 92.5 grams of pure lead. So you see what I'm saying there? That 92.5% efficiency means in that last step, for every 100 grams of lead that we get out of the galena, we actually only get 92.5 grams. We don't get the full 100 grams. So now we have 3 conversion factors that should be able to get us from lead in the final sphere, that final lead that we want, to how much ore do we actually need. I'll set up the beginning for you, and then as you're working on your homework, hopefully you can get the rest of it. So we want, at the very end, 24.2 times 10 to the third grams of pure lead. But we know that it's only 92.5% efficient. So that means that for every 100 grams of that, we only actually get 92.5 grams of actual lead. And then grams of lead and grams of lead will cancel. So then you can keep going. And eventually you want the answer in grams of ore. So those of you who had questions, does that make sense when you do that?
Makes a lot more sense.
Yeah. So when you see these percentages, this is a good way to set that up. This is actually a really important thing, certainly for engineering, but for chemistry as well. When you're setting up chemical syntheses, like you want to build a molecule or you want to do a molecule, make a molecule, we do this all the time. You've got a certain reaction that is like 55% yield. So you have to figure out how much do I need to start with in order to make a certain amount at the end if I'm only going to get 55% yield. And we'll do those calculations when we get into the chemical reactions part of the semester too. So we'll revisit this. But doing this type of a conversion can help you keep all that stuff straight if you have multiple steps and you keep losing a percent each time. Okay. Other questions about mastering chemistry stuff? Or other homework? Okay. The other stuff that's up there right now, Chapter 2 homework is available. Chapter 2 homework is not due until the end of next week, but our quiz on Tuesday will cover the Chapter 2 stuff that we do today. So hopefully you're almost done with Chapter 1, and I would encourage you to start in with Chapter 2 right away so that you get some practice before our quiz on Tuesday. There's also a quiz posted on Mastering Chemistry. On Tuesday, when we come in first thing, we're going to set up computers and do our quiz on Mastering Chemistry. So the quiz that's up on there right now is actually the one we used last year. And so you can get a sense of what a quiz is going to look like, how many questions it's going to have, how does it work in Mastering Chemistry, all of that. It's not for any credit because it's just for practice, but I would encourage you to take a look at that before Tuesday just so you're not surprised at what's on there come Tuesday. The quiz on Tuesday should be similar. All right. Okay. Should we talk about some other stuff now then? We're good? Okay. So moving into Chapter 2 now, which for those of you with different books is the structures of atoms and elements, and the end of Chapter 2 is atomic mass and mole calculations. We'll probably get to that today. So the way the book does it, they kind of tell this story about how atoms were discovered and how we got from the different theories of atoms and all that. And we're going to do that briefly today. I don't think we need to dwell on it so much with all these different laws and things. You can refer to them if you need them for your homework. I don't usually like to put a lot of those types of questions on the exams anyway. But let's just start with what we know rather than starting with what we used to think. So, because you probably already know this. So what's the basic structure of an atom?
Protons, neutrons together, electrons orbiting, electrons.
Okay, anybody want to add to that? Yep. So if we were to split the atom into like two parts, what would be the two main parts? Yeah, I would say probably nucleus and the electrons. If we were to split it in three parts, we'd go protons, neutrons, and electrons, right? All right, so let's look at that. So in the inside of an atom, you've got a nucleus. Which contains your protons and your electrons.
We know neutrons.
Yep. Wow, I'm just not paying attention today. Thank you. Maybe it's all just a test, and I'm just trying to see if you are getting it or not. So protons are positively charged, and neutrons have no charge. Okay. The mass of a proton is 1 atomic mass unit approximately, and a neutron is also approximately 1 atomic mass unit. What's an atomic mass unit? You know how that's defined? Yeah.
The average of masses of multiple isotopes.
Not quite. It's actually the we're going to get to that. That's the atomic mass that we are going to get to. But the unit itself is defined as a 1/12 of the mass of a carbon atom, an atom of carbon 12. So it's an arbitrary definition. It's saying if we have a carbon 12, we're going to assume that 1 atomic mass unit is a 12th of that, and then base everything off of that. So an atomic mass unit ends up being, well, the proton and neutron end up being just a little bit above that because of, the electron also has mass, even though it's just a tiny bit. But it's a way of talking about atomic masses of these tiny things without dealing with grams, because grams are way bigger. So we'll talk later about how to get between atomic mass units and grams using the mole, but for now, we can just talk about that. And then around the outside, we have the electrons. Which have a negative charge. And very, very small mass. So let's see, what is the mass of an electron? About 9.1 times 10 to the minus 28 grams. So even in atomic mass units, a proton to three significant figures, a proton and a neutron are 1 atomic mass unit, an electron is 0.0055 AMU. So let's put that in there. And that means that an electron is a negligible part of the mass of an atom, which means we can usually ignore it. We don't have to worry usually about the electrons because they're orders of magnitude smaller in mass than the nucleus. Okay. Now, one thing to be careful of, and we'll get into this more when we talk about quantum mechanics, but electrons do not orbit the nucleus. What does that mean? Why is that important? Yeah. What does it mean to orbit something? Yeah, to orbit is like a planet, let's say, means to go around something, move around it in a predictable way. So like we can calculate where the planets are going to be at any given time because they follow a particular orbit, they're going a particular speed, and they're on a particular trajectory. Electrons don't do that. They behave very differently because of how small they are and how quickly they're moving, and there are actually some physical constraints as to how much we can know about their motion. So they are not traveling in an orbit. We say that they kind of exist around the nucleus. The technical term for that is an orbital with an AL at the end, so it gets a little confusing. We'll get into that when we talk more about that electronic structure later. But for now, just know that it doesn't actually go around. So all those pictures of like a circle around the nucleus are kind of wrong. All right. But we know those parts of the atom. That's basically what we need to care about here. So how do we get here? Let's look quickly at the history of this, or the structures that came before. So what was thought before we knew anything about atoms, before atoms were theorized? Anybody know?
What elements?
Yeah, so we've got these different kinds of ideas of how things are made. So you've got the 4 elements like air, water, fire, and wind. Is wind one of them? Yeah, and the things are made out of that.
Oh, isn't air wind?
It's a good question. Is it air, fire, water, earth? Is that the other one?
Earth.
Okay, that makes sense. Yeah. So you've got stuff like that. You've got these various different theories about that things were kind of made of their own substances and that there weren't similarities there. And who first developed the atomic theory? You know the name?
John Dalton.
Yeah, John Dalton's atomic theory is what this comes from. Let's talk about those terms really quickly, because they get confused a lot in science. So we've got scientific laws and we've got scientific theories. What's the difference between a law and a theory?
Isn't a law like something that can't be changed, but a theory can be, like, there's no evidence to like change the law. Like, it is what it is, but like a theory would be like you can change it.
Not quite. Not quite, yeah.
Isn't a law something that's been proven to be true in more than one instance, and a theory is something that you think could be true in more than one situation, but it hasn't been proven?
Not quite.
That's like, that's the book.
You're getting there though.
Isn't a theory like open to change if new information comes in, but a law is something that, like gravity, it exists and there's nothing that can change.
So what I'm hearing here from most people is that there's a degree of certainty that's the difference between these two. That a law is more certain and a theory is less certain. And that that's not quite right. They actually speak to different things when we talk about science. So a law is a set of observations a set of usually repeatable observations. So you keep seeing the same thing happen, and you come up with a law that describes that. And this could be about anything. So let's say, like gravity is a famous one. The law of gravity says that 2 bodies attract each other with the same ratio based on their masses and the distance between them. And that happens all the time. We keep observing it. We keep seeing it happen. But we could make more trivial laws too, like when it is nice outside, students come late to class, would be the law of summer classes or something. Because that's just a thing that we see and it just keeps happening, so we'd make a law about it. That doesn't mean that it's certain. That doesn't mean that it doesn't require evidence. We have to keep collecting evidence. So let's say I propose a law of summer classes, and then we start collecting data and we realize, well, actually, it's not that good of a law because people are mostly on time. It doesn't matter, it doesn't seem to depend on the weather. So then we would revise that law and say, well, that's kind of not a great law. Maybe we'll throw that one out, or maybe we'll revise it. Another example of that is Newton's laws of motion. We know about Newton's laws of motion? Yeah?
Yeah.
Like, what are some of the things that they say?
Every action is an equal and opposite reaction, like Newton's law.
Yeah, so you've got these kinds of laws about motion, and we can use those to calculate trajectories and how the planets move and all this stuff. Are Newton's laws always right?
Yeah,
Kind of.
mostly.
They're right in certain scenarios. They actually fail in others. Where is an example where Newton's laws fail? You know?
You know, like the really small.
Yeah, really small things, really fast things, and actually really big things too, when you have to start talking about relativity and quantum mechanics and things like that. So a law isn't necessarily more correct, and it needs evidence, and it can be violated and things like that. So a theory attempts to explain the factors behind the observations. So a theory is proposed explanation of what we're observing. But we're going to say why it happens. Why it is. Notice that there's nothing in there about which one is more correct or more certain. They apply to different things. The theory is actually much more powerful than a law. A law is simply saying this thing keeps happening, and we're going to describe that it keeps happening. The theory says this is why. This is what's causing it. And so because of that, it can then be predictive. We can use the theory to predict new things that might happen as a result of those things. So a famous theory that we're talking about now is the atomic theory. So if we go by that previous definition that theories are sort of like more changeable or less certain than laws, how does that work with atomic theory? Is atomic theory controversial? Like the theory that things are made of atoms? What do you say? Probably not. Again, there's probably somebody who's like got a website about how atoms are a conspiracy and they're not really there.
But everything's
But-
a conspiracy these days.
Well, yeah. So, but I mean, but realistically, most people are in pretty good agreement that that atomic theory is a real thing. And I mean, we've got stuff like this. Oh wait, they've got this new book thing. It's just kind of driving me crazy here. I can't find this stuff anymore. Yeah, let's look at page 46. Here. So the Japanese kanji characters for atom, written with iron atoms on a copper surface. So the blue surface is actually copper atoms, and the little dots that you see in black and red are iron atoms. So is that pretty good evidence that atomic theory is correct? Would you say? I mean, yeah, they're there, right? This is something from something called a scanning tunneling microscope. You're actually not looking at a picture of atoms. So it's not quite right to say that we can see atoms. We're seeing the effects of the atoms on their surroundings. But again, it's pretty good evidence that things are indeed made of atoms. And the entire discipline of chemistry is attests to that as well. So remember that a theory can be just as certain with something like atomic theory, this idea that stuff is made of atoms. That's a pretty good thing. Okay, so the atomic theory comes from two laws you can read about in your book. We'll just discuss them briefly. There's a whole bunch of like problems that you can do with them in the book, but I didn't assign those. I'm just not sure that's really useful. So there were two laws that were described, again, just like things that they kept seeing. And there was no explanation for it, just we keep seeing this effect. The law of definite proportions and these led to the discovery of the atom. So what do these say? Law of definite proportions, and they all, like this one almost sounds dumb now because it's so obvious, but basically all samples of a given compound have this are made of the same proportion of elements. So like if you get some water, it doesn't matter where that water is from. If you decompose it into hydrogen and oxygen, which could be done at the time, this is in the 1700s. If you decompose it into hydrogen and oxygen, you get the same ratio of hydrogen to oxygen every time. Even if you get that water from here, if you get that water from another country, if you get that water from wherever, you always have the same thing. That just seems obvious to us because we know water is H2O, but at the time, that wasn't obvious. Without atomic theory, that's not obvious. Why should water always have the exact same proportion of hydrogen and oxygen? My phone is just blowing up today. So that was kind of the first clue as like, why does this keep happening? Why are these elements always in the same proportions? And then the law of multiple proportions is a little bit more complicated, but let's look at an example. So you take something like carbon dioxide. Actually, let's write it because we don't know exactly what it is right now. I mean, we do, but they didn't at the time. So they had this compound. I don't know what they called it. Probably not carbon dioxide. And then you've got another compound, carbon monoxide. And both of these existed back then. And they could be characterized as different things. So like carbon dioxide was produced by fire, by breathing. Carbon monoxide was also produced by different types of combustion. They knew that they had different effects, like on people or on animals. So they knew they were different compounds. And it was even more obvious with the nitrogen oxides because they're different colors. There's like a brown one and a colorless one and stuff. So let's say we have those two. And you decompose them into carbon and oxygen. That was what chemists loved to do back then because it was one of the only things they could do is you just kind of heat stuff up and you see what comes out and you weigh it. So they could tell that you could decompose these things into carbon and oxygen. So when you decompose carbon dioxide into carbon and oxygen, you always get 2.67 grams of oxygen per gram of carbon. So you break this thing apart and you weigh it, and for every gram of carbon, you get 2.67 grams of oxygen. So that was from this first definite proportions. It doesn't matter where the carbon dioxide came from, what carbon dioxide it was, you always got the same amount of oxygen per carbon. Carbon monoxide, you do the same thing, and you always get 1.33 grams of oxygen per gram of carbon. And this always happened, again, because of the law of definite proportions. You always got the same amount of oxygen per carbon. So they knew these were different compounds, and that one had more oxygen per carbon and one had less oxygen per carbon. But the weirdest thing was, and the thing that really led to the atomic theory, is if you divide those two numbers, you get this nice even integer. And this always happened, and it happened with all different compounds. happened with carbon and oxygen compounds, nitrogen and oxygen compounds, it happened with minerals. Every time they decomposed these things, if you had different compounds that were made of the same two elements but in different ratios, and you did a ratio between them, you came up with these nice even numbers every time, which kind of was crazy back then, because why should there be even numbers every time? Why wouldn't it just come out to some weird number? And the reason it was even numbers every time is because things are made of atoms, and so if you have CO versus CO2, you have to only add things in integer amounts. So this told us that for every carbon, if there were 2 oxygens, or carbon there's 1 oxygen, there's no compound where there's carbon and 1.2 oxygens. That can't exist. So this told them that there must be something going on where there's these little pieces that only connect one at a time, or in integer amounts, and you can't cut them up. And so there must be some particle that you can't cut up. And that's the idea of atomic theory. There's some particle that's so small that you can't cut it up, that it's the smallest thing that you can reduce any compound to. So that's sort of the story of that. Now, of course, we have nuclear chemistry. We know we can't actually cut those things up, but the atomic theory still holds and still allows us to do all of our chemistry and everything. Okay. So do you want to talk about the discovery of the subatomic particles, or you want to just read that on your own or skip it?
Let's talk about it.
Let's talk about it? All right, sounds good. So we know there's three subatomic particles, right? Let's determine first electrons, because that was the first thing that was discovered. Let me get a picture for you. So apparently their book is not have the same page numbers that mine does. That's weird. Okay. This picture. Has anybody ever heard of a cathode ray tube?
Heard of it, don't know much about it.
Yeah, anybody know what it is? You ever seen one before? Yeah, where have you seen a cathode ray tube? Where have you seen one?
My AP chemistry class.
Oh, like an actual tube
Yeah.
thing? Yeah. So you can have it as like a bare tube. But we've all probably seen these. I don't know if you're old enough to remember, years ago there used to be computers and TVs that were like really big and they weren't flat. Does anybody remember seeing those? That's what is inside that. So if you had one of those big TVs or monitors that was really big and long, the reason it had to be big like that was it had this big tube inside. And the tube shot these things called cathode rays, which is what you get when you put a really, really large potential, or electrical potential, between two pieces of metal. You get these rays that shoot out. And these rays can be focused by a magnet. So you can take a magnet and you can pull the rays to one side or the other, which is not something you can do with light, with regular light rays. So that means that these rays are something special, and they knew about them, and they used them, and you can make these screens. And that's why, if you try to take a video of an old monitor, you could see these lines going down it. It's because that's literally what those old monitors did. They had this little ray thing that would really quickly go like this and scan on the screen. And every time it hits a little bit on that screen, it would light up, and that's what makes the picture, or what made the picture. So they had those things. They would use them for stuff like that. And it was eventually discovered that you can control this thing with a magnet, which means that ray must not actually be light. And maybe ray is a bad word, or is the wrong term for this particular phenomenon. And it turns out that what you're actually shooting is electrons. So cathode rays are not really rays at all in terms of light. They're actually electrons. You're shooting electrons off of this metal. And so in doing that, J.J. Thomson and his people in his lab were able to calculate the mass to charge ratio of an electron, meaning how much it could deflect based on its mass and its charge. And that's how they were able to figure out that electrons exist, and these things are actually made of electrons. All right, so then the next experiment, which is a really cool experiment because it's just so difficult, like, to try to figure something like this out at the time. This is called Millikan's oil drop experiment. So what's going on here is you've got some oil in a little jar. And you squeeze the oil, you squeeze like a little bulb here, like a little perfume type thing, through an atomizer, which is just a really small, narrow tube with a narrow opening. And so you're creating tiny, tiny droplets, just like when you spray something in a spray bottle. You have these tiny, tiny, tiny droplets of oil, and then they fall through this little hole one at a time. So he makes this thing that the little droplets of oil are only going to go through one at a time. And then you've got ionizing radiation, like cathode rays, shooting through, or maybe they're X-rays. Does it say? Yeah, it doesn't say what kind of radiation it was. But radiation that's strong enough to knock electrons off of the air. It's called ionizing radiation. And what that did was coat the oil drops with electrons. And now there you've got this tiny, tiny, tiny oil drop coated with electrons that you're watching through a little microscope. This is all done by just by sight, no like fancy instruments to measure these things. He's looking at these things and he's seeing these tiny droplets fall down. They're getting coated with electrons. And then he's controlling the voltage between these two plates so that the oil droplets actually get suspended. Because the negative plate is on the bottom, electrons are negative. And so depending on how strongly negative that is, you can repel the oil droplets because they don't want to go onto the negative. And by just controlling that and watching how far and literally like timing how quickly they would fall, he could figure out exactly what that charge was. And then once you knew the charge, you can calculate the mass. So just with this like little apparatus that he's looking in and measuring by hand with like a stopwatch, you can figure out what's the charge of an electron and what's the mass of an electron, which, I don't know, seems kind of cool from how you can measure that with relatively primitive equipment. So from that, we know there's electrons, we know the mass and the charge of the electron. So what's next? What's the other part of the atom that we need to discover? Yeah, the nucleus. So the nucleus is discovered kind of by accident. Well, not by accident, but through a different experiment that didn't turn out the way they had expected it to. So I don't want to put this on the notes, but if you look at this picture in the book, once electrons were discovered, this is what we thought. This is what they thought atoms were. That atoms were this kind of sphere of diffuse positive charge, and the electrons were suspended inside the positive charge. So no other particles, there's just electrons, but the rest of the atom is this kind of positive blob. And that was called the plum pudding model. So to confirm that, they did this experiment where they shot these radioactive particles known as alpha particles through gold foil. And what they assumed was that the alpha particles would simply travel through the gold foil and hit the back. And if they did that, that would be confirmation that it was a correct model of the atom, that this plum pudding model was actually correct. Instead, they didn't see that. And they found that there were these deflections, sometimes way back this way. But most particles went through, but then a bunch of them would deflect. And so they thought maybe there was something wrong with their setup or something, but they kept seeing it, kept repeating it. And if you're a good scientist, it means that you go back and you revise what you thought before. So instead of that plum pudding model, what this means is there must be some actual positive particles in there that are allowing these alpha particles to bounce off, because alpha particles are also positively charged. So there must have been some sorts of things in there that were allowing this thing to bounce off. And that became the discovery or the proposal of the atomic nucleus. That if you had your positive charge concentrated in this nucleus, and then you had your electrons kind of on the outside, Most of them could pass through that space between the nucleus and the electron, but every once in a while, one would hit the nucleus and bounce off and be deflected. And that explained this experiment. And so that's how we now have that modern structure of the atom. And then in a few chapters, we're going to talk about when this gets revised. We talk about quantum theory of how the electrons are arranged. But that gives us our basic structure of what the atom looks like. Incidentally, do you have any sense of how far these things are from each other? Like, let's go back up to our picture over here. We always draw atoms like this with the nucleus in the middle and the electrons around the outside. Any idea how far apart those are?
As far as I know, the nucleus is really packed together and the electrons are stupidly far away.
How far is stupidly far?
Like I heard something about like it's like an atom size of a football field, like the nucleus would be the size of a quarter or something like that. Heard that? I don't know.
Yeah, I think it's even bigger than that. So the nucleus is about 10 to the minus 14 meters. So let's put this here. The radius of the nucleus is 10 to the minus 14 meters. The distance between the electron and the nucleus, and this is different for each atom, I'm just saying on average. About 10 to the minus 5 meters. All right. So let's think about how big that is. That is 9 orders of magnitude, right, between -5 and -4. Wait a second, no, that's wrong, I'm sorry. Let's call that so atomic radius is about 10 to the minus 10 meters. Sorry, that flipped. So that's 4 orders of magnitude. That's 10,000. So that means if our, is there a meter sticking here? Yeah. If this is an atomic nucleus, if this is the size of an atomic nucleus, the closest electron, or the outer electrons, are about 10 kilometers away, which is about 6 miles away. So that gives you a little bit of sense of the scale. If it's this big, our electrons are 6 miles away, which is a lot. So the consequence of that is that what is most matter made of? Like, what is the volume of most matter taken up by?
Empty space.
Empty space, yeah. So most of everything is just empty space between the nucleus and the electron. So I don't let that scare you when you're standing on something really high, like on a bridge or something, that mostly what's under your feet is just empty space. That the bridge is made of empty space. No, not interesting. That kind of blows my mind. I don't know. Think about it next time you're high, it'll be better. Okay, so we've got our atoms. Let's do some calculations with them. So take a look at this sheet. Anybody's got one of these? A couple other things that we need to talk about with regard to different types of atoms that don't quite fit in the description that we have so far. So first, what are isotopes? You heard that word before? Yeah.
Atoms that have different number of neutrons compared to protons.
Right. Atoms with the same same number of protons. But different number of neutrons. All right. So the way we express this is like this. Let's take carbon. We can say, put a C there, which is a symbol for carbon. And we also often will put a number down here to the lower left. Which tells us the number of protons. And we call that the atomic number. And then we can express what type of isotope it is by reporting the mass. The mass number is the sum of the protons and the neutrons. So if we take those two numbers together, we subtract them, we can see that this particular isotope of carbon has 6 neutrons. Notice that these are always whole numbers. These are counts of the numbers of protons and the numbers of neutrons. So if we had other isotopes of carbon, they would all have that same 6, but they could have different numbers of neutrons. Isotopes, that word isotope signifies a relationship between things. So we don't say that carbon-12 is normal and the others are isotopes. We say those are all isotopes of carbon. Or we can say that the two of them are isotopes of each other. So the same atomic number, the same mass number, which is our protons plus neutrons. So we can determine the number of neutrons from that number. All right, how does that differ from the number in red on the periodic table that we see up there?
Isn't that the average, like, you were take the average of their commonness?
Yes, so let's take a look at that. This is a common mistake. So if you look at the periodic table, you've got a C here, you've got 6 up here, and then this number underneath is 12.011. So there's a tendency to, if I ask a question on an exam like, how many neutrons are in this carbon atom? There's a tendency to look at the periodic table, see that 12 underneath, and say, okay, well, it must be 6. But that number is not a mass number. That is not an integer that tells us a count of protons and neutrons. This number is an average. It is a weighted average of naturally occurring isotopes. So the way that works, the way that calculation works, most of the carbon in the world is carbon-12. In fact, it is 98.93%. There's a little bit of carbon-13, 1.03%, and just a little bit of carbon-14. So little we don't even need to mess with it unless we need more significant figures to worry about that, because it's like
It's like 0.04.
0.04%, is that right? 0.04 or 0.04%?
0.04%.
Yeah, so small. So the weighted average would look something like this. just like when I calculate grades or when you try to estimate grades, you take the percentage multiplied by whatever amount you're weighting, so in this case 12, and you add it to the other one. So the reason that's a weighted average, a perfect average or a non-weighted average, is you add up the different things and you divide by the number, just like you did in lab yesterday. Another way of saying that could be, like, let's say we wanted a 50-50 average of these two, a perfect average. We go 12 plus 13 divided by 2, or we can think of that as 0.5 times 12 and then 0.5 times 13. So in a weighted average, you change those amounts so they're not 0.5. In this case, it's mostly 12, so we move that up to 0.9893, and then it's less the other one, we move that way down to 0.0103. And if we add those up, this one comes up to 11.87, this one comes up to 0.139, and so with our significant figures, this comes out to 12.01. So we're making a weighted average of the naturally occurring isotopes to get our number that we see up there. That's our more useful number from a lab standpoint, because we're not picking out individual atoms when we weigh carbon. That would be impossible. It would be too small. We don't have any tiny atom tweezers. They do in those microscopes, but it's not useful for chemistry. So we can kind of pretend that all of our carbon is 12.011, even though we know that each individual atom has to be an even integer number of either 12 or 13 or 14. So those are averages. And the reason that we can get messed up by that is a lot of atoms on the periodic table, those averages don't even approach their actually naturally occurring values. For instance, let me find the numbers for this example. So let's look at, well, they don't have them here, but I think I know the numbers. Let's look at bromine. So if we look at the periodic table, bromine has an atomic number of 35 and a mass of 79.904. I'm just copying that from the table there. So if you looked at that, you might think, okay, 79.9, that's pretty close to 80. So probably the most common isotope of bromine is 80, which would have 45 neutrons, right? 35 protons, 45 neutrons. Well, in reality, bromine 80 doesn't even exist. The two common isotopes of bromine are bromine 79 and bromine 81. And they're approximately 50% each. So when you average those two isotopes together, you get 80, around 80, which is what we see on the periodic table. But there isn't actually any bromine 80 that exists. It's not a real isotope. It's the average of the two that leads to that number. So that means that if someone's asking you the number of protons or neutrons in something, they have to actually tell you what the mass number is. You can't get that number from the periodic table because that number is just an average. All right, let's try a problem with these, and then we'll take a break and come back and do some more. So take a look at number 14, the very last one. We're going to look at silicon, and it's 3 naturally occurring isotopes. So see if you can do a weighted average and figure out the atomic mass of silicon. 14, the very last one on the sheet. And it's a multiple choice one, so you can check. See what answer you would pick. Yeah.
Yeah, there's no question there. That's really the question.
Do you have any good ideas for questions for that one? Okay.
Yeah, I bet it's which two are isotopes?
Oh. So that is this one.
I don't know. Oh, okay. Yeah, maybe it's not. Actually, it looks like you did it right. Oh, it's because you gotta use these numbers, it's just a significant figure. And I can fill it up with this one. Because you gotta use these masses.
Okay. So then,
But you did it right.
okay.
All right, let's look at this one. So, if you did it exactly the same way that we just did it with carbon, you use these whole numbers. That actually ends up not quite working when you look at a lot of significant figures, just because the AMU is not, or every element does not have an integral AMU. So you look at these are like the AMU, the mass of silicon 28 is pretty much 28, but out to more than four or more significant figures, it's not. And that's just because of what an atomic mass unit is and some other characteristics of the atom. So, so we have to take that into account. So the right way to set up this calculation then, if you're given those, most questions you'll just have the whole numbers, but this one you're given those masses. So you would use that mass instead. And that's going to be, oops. Like that, so you'd weight that 92%. The next one, 28.976495, gets weighted 4.67%. And then the last one, gets weighted 3.10%. So, what'd you get? Let me get this one. But D, what is that? Oh, here, 28 point. So that's our average. That's our average for silicon. If you did it with the integer numbers, you get a value that's a little bit bigger than this, right? Like 28.1 or something was what you got. So you could still probably guess that that was the closest one, but it wouldn't have been quite the same just because of the slight difference in the masses. All right, let's stop there and take a break. As you're doing the break, also take a look at number 13, the question just above it. It's the same type of question, but instead of asking for an average mass, it's asking for the abundance. So you're solving for one of these values. So just kind of work at that as you go and get lunch or whatever. We'll start back in about 15 minutes. What are ions?
Positively charged elements, oh, not positively charged, but like charged elements.
Yeah. How do atoms become charged? Or what is it about atoms that could make them charged? Have a charge, have an overall charge? Yeah.
Their whole thing.
Yeah, so what's happening there that's making that an overall charge? That's right, that's how we get it. What's happening in that? Go ahead.
Additional removal of electrons.
Yeah, losing or gaining electrons, or we can just talk about it in the, like what it is. Charged atoms have let's say unequal quantity of protons and electrons. Is unequal a word?
Yeah.
Unequal, unequal? I don't know.
Unequal.
Okay. So a neutral atom is always going to have the same number of protons and electrons, which means an ion is going to have a different number of protons and electrons. Okay. The important thing to remember about that is just that if we change the number of protons, we change the identity of the atom. So when we're making ions, we only change the number of electrons. So let's look at that. If you have, let's say, a lithium atom, let's say it's, let's be specific here, we'll call it a lithium-7, since we were just talking about that. So if you have a lithium-7 atom, what are the quantities of protons, neutrons, and electrons? How many protons do we have here? 3, which we can look up on the periodic table. So 3 protons. How many neutrons? 4 for lithium-7. Again, we can only know that number if we're told the mass number up here. If I just said lithium, how many neutrons does a lithium atom have? You can't tell me that answer. Periodic table doesn't tell us that. So I have to specify that mass in order to ask that question. And then how many electrons? 3, because again, it's a neutral atom, so we need the same number of protons and electrons. Okay. What about lithium-7 plus 1? What's changed? Yeah. Number of electrons has changed. So we've still got 3 protons and 4 neutrons. How many electrons now? 2. How do you know it was 2?
Because when you did it, you removed in order to do that, or like.
Yeah, right, exactly. Protons are positively charged. Electrons are negatively charged. So if there's one more proton than electrons, that means it's going to have an overall positive or +1 charge. Same thing works with negative. So let's say we have bromine 79. How many protons? 35. How many neutrons? 44, yep. And how many electrons? Shout out, yeah, 35. Because it's got to have the same number because it's neutral. Okay. Now, if we've got bromine minus, we still have 35 protons. We still have 44 neutrons. How many electrons? Yeah, 36 in this case, because we've got -1. So we need one more electron since those are the negative charges. Okay. So extra electrons give us a negative charge. Fewer electrons give us a positive charge. We don't want to say extra protons because we don't add protons. Protons always stay the same. All right. Now, a nice thing about ions is we can predict what sort of ions a lot of elements will form. And we'll get in later when we talk about like electronic structure and how you exactly you do electron configurations. But just as a basic guideline for us, let's draw a little periodic table here. Anybody know any kind of shortcuts or help about how we can use the periodic table to figure out ionic charges? Yeah.
The first group is +1, and the group is +2.
Yeah, that's one. So we can know what some of these charges are generally. Let's separate it first very generally. So if you look up at that periodic table, you see this kind of stair-looking thing, which I didn't quite draw right. Let's see. I like that. I don't know what. Anyway, is that right? What does that mean? What does that mean?
Separate the metals and non-metals.
Right. So everything over here on the left, to the left of that stair, we call metals, and everything over to the right, we call non-metals. So what does that have to do with charge, with ionic charge? If you were to like have a general rule of thumb, what can you say about charges of metals versus charges of non-metals?
Charges of metals are positive. I don't know.
Yeah, no, you're right.
Charges are positive, charges of non-metals are negative.
Right. So if these things are going to make ions, the metals are usually going to make positive ions. The non-metals are usually going to make negative ions. Now, of course, there's always exceptions, and we'll talk about oxidation states, which is a little bit different than charge, but that's kind of a general thing. And there are a few columns that fit pretty well that always tend to have the same types of charges. So as you said, over here in the first column, these are usually +1 charge. These are usually a +2 charge. In fact, with those, I would say they always are if they're an ion. They could be neutral or they can be that charge. There are some others that are pretty commonly the same types of charge. If we look over here at the halogens, 7A are usually -1. The next ones, the chalcogens, are usually -2. Others get a little less certain about that, but that's a good way of just generally remembering those. So name-wise, let's look at some names. Anybody remember what is the name of this first column here, the +1s? Yep, those are the alkali metals. +2, we've got these.
Alkaline earth metals.
Yep, alkaline earth metals. What about the ones in the middle? Yep, those are the transition metals. We talked about the halogens. The next column over, below oxygen, are called the chalcogens. And then the very end, anybody know those? Yeah, those are the noble gases. There are some other little names for ones here and there, but this is fine. Down at the bottom, We got these things. What are they called? You know those? Would you say pyridines? That's different. No, it's okay. There's a couple different names for these.
Those are the two ones that are down there.
Yeah.
And it's like lanthanide activities.
Right. So they've got little stars up there. These are called the lanthanides, also known as the rare earths, the rare earth metals. So the active. So if you hear that term rare earth, it's often connected to magnets. So you can talk about like rare earth magnets used in speakers or in other kinds of components like that. Those are magnets made of those elements in that row. If you haven't noticed how that flows before, I can show you. So those little stars mean that this whole block of lanthanides and actinides is meant to fit right here. So imagine this space between here and here kind of splitting open, and that one goes way down the wall, and then these would fit right in between. So they get dropped down just because that would make a really big, unwieldy periodic table. This way it condenses a little bit, but if you follow the numbers, you count up, and then jump down here, count through those, and then come right back here. Okay. When we get to electron configurations, we'll talk about what that means. All right. So ions can gain and lose electrons to become these various charged particles. And we can count the numbers of subatomic particles in them. Yeah.
I just got a quick question.
Yeah.
When you say the rare earth metals,
Mhm.
how rare are they?
They're actually pretty common. Yeah, it's not a great name. They're not that rare. They're not that expensive, which is one of the reasons we use them for stuff.
Everywhere.
What?
Like everywhere. Right?
Yeah. Well, yeah. I mean, many of them are very common. They're mined. They are so widely used that there's some risk that we could deplete them because they're used in a lot of modern electronic applications and things like batteries and other types of newer technologies. So they're in our cell phones and computers and things like that. So they're not a renewable resource because they're just elements that are in the ground. Unless a big planet or an asteroid full of those crashes or something, we're not going to get any more. But they're not really that rare. They're not as rare as some of the precious metals like gold and silver. Some of the transition metals are actually quite rare. Iridium, ruthenium. Ruthenium's not that rare. Rhodium's a little more rare. So they're less rare than those. Generally. I don't know why they were named that initially. I imagine it at the time they were discovered, they were pretty rare. And if you look at some of the different colors and things in the periodic table, what does that represent? Like the outlines or the blue or the red letters. You know those? Yeah.
Well, the outline symbols are the man-made.
Yeah, the outline ones are man-made, so they're not naturally occurring. I mean, they can be naturally occurring like transiently, but they're radioactive, which means as soon as they exist, they break down and start decomposing. The black ones are solids, the blues are liquids, and the reds are gases at room temperature, standard pressure. So that is the periodic table organization. You'll notice the two numbering schemes on the top. The green one is the older one with the A's and the B's. It's not a great classification scheme, and so the International Union of Pure and Applied Chemistry, the naming body, the official chemistry body, has replaced them with those column numbers 1 through 18. We still sometimes keep those old numbers up there because they can help us with some things like counting electrons. We'll get to that later. But the newer numbers are the just numbering them 1 through 18. All right. So any questions about ions or periodic table organization? We're going to get way more into this when we get into electrons and properties toward the end of the semester. This is just kind of a basic introduction of that. All right, then let's get to the last part, which is talking about masses. Okay, who's done these types of calculations before? Hopefully everybody calculated some molar masses. We'll go through it, of course, but what is the point of it? You know, everybody knows there's this mole associated with chemistry. You probably even remember the number, maybe or maybe not. But what is it for? What's the point of it?
Isn't it to make the units of things similar?
Yeah, I mean, that's the idea. Like, in what way? How do we use it to do a kind of a unit conversion that's important when we're talking about something like atoms and molecules? What is important about it? What are we changing here? Let's talk about the number and then we'll look at what that's for. One mole of anything. Does anybody remember that number? And are there any units on that number?
No.
It's just a number. Yeah, so it takes whatever units we need it to take. So for instance, it's simply a way to count things. So if we had a mole of atoms, we would have that many atoms. It's often described, the way I kind of think about it, is a number that we understand a little bit better. If we had a dozen atoms, how many atoms would we have? 12. So the mole is a word that represents a number. And it allows us to count using that number. So let's say you own a donut factory. Does anybody own a donut shop? You bring us donuts? No? Okay. So let's say you have a donut shop and you're tracking all the donuts that you're selling, whatever, and you sell them by the dozen. Maybe it makes more sense to count in dozens than in individual donuts. Let's say you're only selling them by the dozen. So it makes a lot more sense in your accounting sheet to have, well, today we sold 300 dozen donuts instead of 3,600 individual donuts. And that's exactly what the mole is for atoms. Atoms are small, extremely small. So to count them individually is basically impossible. So we need a number that allows us to understand the atom, or how we can count atoms without actually physically counting them. And that's the number that we use. So one individual atom is not something we can really experience. But this many atoms is like a handful or so, depending on what you're talking about, depending on what kind of element you're talking about. So it's a way for us to translate from the tiny scale to a scale that we can understand. So if we want to count atoms, but we can't individually count them, how can we use that mole idea to count them?
So geometry.
So like, what does that mean? How?
Is that just doing all like kind of like unit conversion sort of stuff?
Right. Well, we need to know. Let's look at an example. All right. So has anybody ever seen one of those things like in a store where there's a big bottle of like jelly beans and you have to guess how many jelly beans are in there and then you win? Has anybody ever won one? Yeah? What'd you win?
A cake.
A cake? What'd you have to guess?
How many beads were in a jar?
How many beads were in a jar? Do you remember about how many there were?
I don't remember.
Was it like thousands or
It was-
hundreds?
It was like 100 because they were big beads.
Oh, okay. Okay. So, yeah, all right, well,
But you want a cake,
congratulations.
Good for you.
Yeah, you want a cake? Was it a good cake?
No, it was trash.
Oh, I'm sorry. Story took a dark turn.
Yeah.
All right, so let's say you like guess, so let's say there's like a giant one. Like you've got an entire huge garbage can full of jelly beans, and you got to guess the number of jelly beans. And so do you think that someone in that store is responsible for actually counting all those jelly beans individually? Probably not. How do you think that they'll figure out how many are in there?
I mean, that's it.
Yeah, so you could, well, assuming they knew that, yeah, that would be one way to do it. So you go by the bag instead of by the individual jelly bean. How else?
The amount of space one jelly bean takes up, and then the amount of space you're putting them in.
Yeah, you could do it by space. You could say, okay, the jelly bean takes up this much space. When it's full, then we've got this much volume in our container. That's a little tricky because the jelly beans might not pack together really well, so you've got a bunch of empty space that you're not really accounting for there. What's another way we could do it?
Yes.
Mass, yeah, we could weigh it. Is that what you're gonna say too? Yeah, you could weigh one jelly bean. You could say, okay, one jelly bean weighs a gram. So if the whole thing weighs 100 kilograms, then you know there's 100,000 jelly beans in there. And that's exactly what we do with atoms. So we define this molar mass as this. So we define the molar mass as the mass of that many atoms in grams. And then we can weigh something and know how many moles of atoms there are there. And handily, the thing that really makes this work well is that we also set this number equal to the mass of one atom in AMU. So that's not part of the definition of molar mass, but that's the same number. So the mass of one atom in atomic mass units is the same number as the mass of a mole of atoms in grams. And that's how we use that red number on the periodic table. So we look back up at carbon, it says 12.011. That's the mass of an atom, or the average mass of an atom in AMU. But that's also the mass of a mole of carbon atoms in grams.
Is that by coincidence or by purpose?
By purpose. That's how Avogadro's number is defined,
Okay.
in order to make that work. That's where that number comes from. So 12.011 is the average mass of one carbon atom. So that would be 12.011 AMU. And it's also the mass of 6.02 times 10 to the 23rd carbon atoms, which is 1 mole. Now 12 grams of carbon, that's like a reasonable amount. That's about a handful of carbon. So that's an amount that we can deal with, whereas a single carbon atom is not an amount that we can deal with. We can't count individual atoms. It's interesting that this is in this chapter. I'm not really sure. I think it fits a little bit better later, but we can talk about it now. Because the reason this is important is when we talk about chemical reactions, molecules react with each other counting-wise. Like, think of some reaction like H2 plus O2 yields H2O. You have to count individual molecules and say 2 of these and 1 of these comes together to make these. And so using the mole concept is how we count those atoms on a large enough scale that we can actually do it, that we can actually weigh it out and plan out our reactions. And that's kind of the point. All right, so let's practice how we do some calculations with this. We'll just write it down here. How many copper atoms are in a copper penny? We'll assume it's a pure copper penny, an old one. With a mass of 3.10 grams. So this is the atom version of the jelly bean thing. We've got a penny, it's got a bunch of copper atoms in it. It's not practical to count the individual copper atoms. We can't get to that scale and count the individual atoms. So we have to say, all right, how much does each atom weigh? And how much does this overall thing weigh? And therefore, how many of them are there? So we're going to use the mole to figure that out. We can set this up just like the conversion factors or the conversion questions we've already been studying. There's nothing new about using the mole. It's another type of conversion factor. So we can say that we know that 1 mole of, we'll just say Cu, copper atoms, and we also know from the periodic table that 1 mole of copper is 63.5 grams. So those equalities we can use to convert in the exact same way that we just did those other questions, those other problems. So we can make a plan and say the grams of copper, we're going to turn that into moles of copper, and then we can turn that into copper atoms using those equalities that we just wrote down. So the same thing as those other types of unit conversions, we're just using a different quantity now. We set that up the same way. So we have, based on the question, 3.10 grams of copper. And we're going to go from grams of copper to moles of copper. The abbreviation for moles is MOL. It's not much of an abbreviation because you only lose a couple letters, but that's what it is. So we cancel grams of copper, and then we can cancel moles of copper and get atoms. So let's use those equalities to fill those numbers in. The molar mass tells us that there's 63.5 grams of copper in every 1 mole. And Avogadro's number, that mole number, tells us that there's 6.02 times 10 to the 23rd atoms of copper in every mole of copper. So we cancel grams of copper, we cancel moles of copper, and we're left with atoms of copper. So I don't have scientific notation on here, so I'm just going to add that. I multiplied 3.10 by 6.02 and divide by 63.5, and then I'm going to add that in. So that'll be 0.294 times 10 to the 23rd atoms of copper. Proper scientific notation, if you're really being careful about it, you always have one number before the decimal place that's not 0. So we would move this to 2.94 times 10 to the 22. For me, when you're like doing quizzes and exams and stuff, I don't care if you don't do it that way. But technically, true proper scientific notation should use that second style. And if you do it on your calculator, it'll just do that for you anyway. So. All right, so now we've counted the atoms of copper in this particular penny by using that molar mass. Okay, let's try another one. There's only a few different ways this thing can be asked. So if you do a bunch of practice with these molar mass problems, you're going to encounter every possible thing. So here's another way to ask it kind of backwards of how we just did it. A 20-gram sample of an element contains 4.95 times 10 to the 23rd atoms. What is the element? But for this one, talk to the person next to you or the people at your table and see how you would go about this. You're given a mass of an element and how many atoms that is. You figure out what the element is. So to help us get started here, what are we really solving for? What's going to tell us the identity of the element?
The molar mass.
The molar mass. So the thing that we're going to end up, that we want to calculate at the end is the molar mass. So how can you solve for the molar mass? That's going to be the end of your conversion. It's the molar mass. The grams per mole.
Yeah, right, because no matter how I define this, it just is this one. The answer to the word. No, because what it's doing is. Your order of operations is still wrong. You have a. That is some communication. Those numbers. Go forward.
All right, let's take a look at this one because it's a little trickier. So we want to identify the element by its molar mass. We know the units for molar mass are grams per 1 mole. Because molar mass is how many grams are in 1 mole. So grams per 1 mole, which means we need to divide a gram by a mole. So we've got a gram, we know the mass of the sample, but we don't know the moles, we know the atoms. So how can we convert atoms to moles? Yeah, that's how we're going to use Avogadro's number. So we're going to go 4.95 times 10 to the 23rd atoms. And we know how many atoms are in 1 mole. We know that there are 6.02 times 10 to the 23rd atoms in 1 mole, which tells us that this is 0.822 moles. Now we can calculate the molar mass by dividing grams by moles. So 20.0 grams divided by 0.822 moles is 24.3. We looked that up on the periodic table, and that looks like magnesium. Is that what you got? Maybe? Let's look at another way to do this that makes it look more like a regular conversion program or problem rather than trying to work that out that way. The other way to do this is to say, well, we've got grams and we've got atoms, so we can get grams per atom. How do we get grams per mole? So grams per atoms would be 20.0 grams per 4.95 times 10 to the 23rd atoms. And then we want to convert that into something that is converting atoms to moles. Use that same conversion factor. We cancel atoms, and our final answer here is going to be in grams per moles, which should give us that same number. So grams per mole is what we're looking for there. All right, let's keep working on this. How many helium atoms are in a blimp containing 536 kilograms of helium? So again, this is the jelly bean problem. We got a blimp with a whole bunch of helium in it. We're not going to count all the individual atoms. So how can we count the number of helium atoms in that blimp using the mole concept? Do that one I try. Yes. Yeah, remember the molar mass on the periodic table is in grams. So we have to convert from kilograms to grams in order to use that.
I don't know. Is that? Seems reasonable.
Alright,
That one I
I'll
should.
take it.
I'm just thinking like magnitude wise, like how, about how big would it
I
be?
think that
That's about right.
sounds reasonable.
I don't know the answer to that. So if you got an answer, talk to people around you, see if your answer is free, or if not, what you might have done. differently. You know, if you need a hint.
All right, what kind of numbers do you get for this one? You want to throw one out there?
8.07 times 10 to the 20th atoms.
Yeah, does that sound right? See a lot of head nods. Yeah, let's set this up. So we're going to go kilograms to grams to moles to atoms. We can always get atoms from moles by using Avogadro's number, and then we can get from grams to moles using the molar mass. Kilograms to grams, we know our metric conversions. So that's going to look like 536 kilograms. So we're going to go kilograms to grams, grams to moles, moles to atoms. So it's 1,000 grams a kilogram. Helium is 4.00 grams per mole. And we know we've got 6.02 times 10 to the 23rd atoms per mole. (806,680), which is 807 to the 8th, 28th. Or 807 to the 5th, so to the 28th, yeah. Questions about that one? Laying out your answers like this, or at least kind of in order, is always a good idea. It just kind of keeps all your information straight. And then when you're doing exams and you're writing this stuff up, I like to be as generous as I can be with partial credit. So if I can see all the stuff you did, and I see that you just got like one number wrong, but everything else is set up right, I can still give you most of the points. If your stuff is kind of all over the place, or if you just do it on your calculator and you write down the answer, I can't really help you out if it's wrong. So it's always a good idea to keep yourself organized and try to have your work laid out. It only really helps you. Even when you're going back and checking your work, you can find mistakes more easily if everything's laid out in that way. Are you gonna try another one? Maybe, maybe not. No, not worried about it. All right, well, we've got about, what, 25 minutes of class left. So if you want to stick around and try a couple more, you're welcome to. If you don't have to. Just keep in mind, quiz Tuesday. Work on that mastering chemistry. The quiz will be on chapters 1 and 2, which is measurements, conversions, atomic structure, mole concept, all the stuff we did in the last few days. Everything we've done this week. All right, for those of you sticking around, let's take a look at Hi. Get this thing loaded up again here.
We got another lab on Tuesday, correct?
No, lab on Wednesday.
Oh, yeah, Monday. Okay.
Yeah, because there's no class on Monday.
Yeah, I keep forgetting that we have labs on Mondays.
Okay, let's take a look at, have a good day, this here. So let's make sure we're good with our atomic structure stuff. And then we'll go back into some more moles and things. So see if you can complete this table. In each case, you've got a symbol, you've got an atomic number, A is going to be your mass number, and then protons, electrons, neutrons, and charge. So again, we have to be given some of this information to fill in the rest of it. Hopefully they gave us enough in each case. Looks like they did. So see if you can complete that table. Z is atomic number. A is mass number. Hard to see. All right, I'm gonna start filling this in. Stop me if you have a question about some of them. Or if I get some of these wrong.
For sulfur number of electrons.
Yes. Yes, you're right. Sorry. 18. Did I get any more wrong? Good. Any of these that you don't understand why I put a number somewhere that I did? No? All good? All right. Is this what you got also? Mostly? Yeah. Okay. What other topics from today or before would you like more practice with before we go today? Should we go back to the molar mass stuff?
I'm still a little confused on how you got the mass number.
Sure. The mass number is the protons plus the neutrons. So the sum of the protons and the neutrons. In this case, we're given the mass number and we can calculate the number of neutrons from that. But you always need to be given either the mass number or the number of neutrons. If you're missing both of those, you can't figure that out because there could be different isotopes. That's how you're told which isotope we're talking about. All right, let's do some masses. This is kind of an interesting one. I think this is in the master in chemistry also, but that's okay. Just do it now. The mass of an average blueberry is 0.7 grams. The mass of an automobile is about 2,000 grams, 2,000 kilograms. Find the number of automobiles whose total mass is the same as a mole of blueberries. So think about what we're doing here before we start here. We're using the mole to count them. So we're saying this particular number of blueberries, how much does it weigh? And then how many automobiles would weigh that same amount? Starting with mole of blueberries. I'll set this up and I'll let you go out of here. And ending after some steps, however many there are, with let's just say cars. So you can either think forwards or backwards or both. What can we turn 1 mole of blueberries into? And then what can we get to number of cars? It may make more sense to you to do it in separate steps and not do it as one big conversion. That's fine. However you want to think about it. Let me know if you're stuck.
blueberries. Right, so you go this, it takes the whole, so you go bowls of blueberries, number of blueberries, and then number of blueberries, grams.
Think about it. Start it out that way and see if that makes sense.
Should we try this or you're still working? What? Give it a try? Okay. So if we go with the strict like conversion idea, I guess let's try that first. Maybe you did it a little bit differently. So I'm gonna go moles of blueberries. And then I think about like, what do I need to turn that into? Well, if I've got a mole, I need to know how many blueberries that is. So that's gonna be number of blueberries. We'll say BB. If I know the number of blueberries, I can get the mass because I know how much each blueberry weighs. That's going to be the same as the mass of the cars because that's what the question says. How many automobiles is the same as a certain number of blueberries? And then I can get the number of cars from the mass of cars because I know how much each car weighs. So let's set that up. One mole of blueberries. So I'm going to cancel mole of blueberries and instead get number of blueberries because I know that there's this many in a mole. See that step so far? Then I can cancel my number of blueberries and instead have a mass. And I'll not label that because we're going to go between blueberries to cars. So we're just going to say total mass because I know there's 0.75 grams in a blueberry. So now I'm going to turn that into cars. And we know that there are 2,000 or what? 1,000 kilograms. So we have to convert between grams to kilograms. So that's going to be 2.0 times 10 to the 6th, because it's 10 to the 3rd kilograms. So it's 10 to the 6th grams. If you don't see that, you can do an extra step where you've got 1,000 grams per kilogram per each car. So that's going to be 6.02 times 10 to the 23rd times 0.75. I'm skipping the times 10 to the for now because my calculator doesn't do that. All right, so that's going to be 2.26 and then times 10 to the 23, but divided by 10 to the 6th, which is 17, right? 2. Carbs. So still a lot of carbs. Is that what you got? Have you tried it in the calculators? Okay. Sure. So the other way to think about this, rather than trying to set it up in this whole line of conversions, is to think about what's happening. You've got a certain number of blueberries that weighs a certain amount. Calculate that first, and then figure out how many cars would be that same amount. So you're still doing the same calculation, but you might kind of draw yourself a picture or something and say, okay, here's my blueberries. 1 mole of blueberries. I know that that's 6.02 times 10 to the 23rd blueberries times 0.75 grams per each blueberry. So that gives me my total mass. That's going to be my total mass of blueberries. Then you could say, all right, if I had a thing of cars that weighed that same amount, how many would there be? We go over here. We've got cars. And so on. And we've got 4.52 times 10 to the 23rd grams of cars. And then we would use that same those same numbers. So we've got 1,000 grams per kilogram. We've got 2,000 kilograms per car. And that should give us that same number, 2.23 times 10 to the 17th. It's going to be not quite the same because we rounded over there, but it'll be sort of close. So 4.52 divided by 2 is, so we got 2.26, but close enough. All right. I know these are tough. There's a lot to think about. Really, practice is the biggest thing. There's only so many of these types of problems. So go through the Mastering Chemistry, but also if you still feel like you need practice, go through the book problems. There's hundreds of problems in the chapter that are not on Mastering Chemistry because I don't want to give you that much, but you can do them. There's also actually in Mastering Chemistry, there's an open assignment of all of the problems in chapters 1 and 2. It's not for credit, it's just for practice, but they're all there. So if you want extra practice where you can actually see the answer right away, they're all there, and you can just keep working on them randomly.
I just have a question.
Yeah.
Yeah. Is it asking for the original or the
Yes.
actual?
The original, like, go 5 and 5. So it's yeah.
Do you know where there's a UPS
don't.
You can look it up. Let's look it up.